Next, let's analyze the second part of angle XPY. So let's first think about it, how it is constructed. So first, let's understand what is point P. Actually, point P, I'm claiming that this is the midpoint of arc BC. Why this is the case? So let me take out that component for you. So here, angle XPY, yeah. So let's see, this is the circle. And here, this is the angle bisector. The bottom point is P, right? So each half angle is A over 2. So now let's look at arc BP. So one is the inscribed angle is A over 2, is BAP. Another inscribed angle is BCP. So these two should be congruent. So this is A over 2. Okay? And then let's look at arc CP. So CP has one inscribed angle is angle CAP. Another inscribed angle is CBP. So they should be congruent. Both of them have degree measures A over 2. So now we have proved that P is the midpoint of arc BC. And in addition to it, we further shows that triangle BCP is a isosceles triangle, and we exactly know angles PBC and PCB. So it tells us that we can exactly locate P and fully characterize this triangle and fully characterize the position of P. And also exhibit some symmetry, right? Okay, so we know exactly the place of P. And next, we need to locate X and Y. So at a high level, this is the structure of triangle BCP and X and Y. So this is triangle BCP. It's a southern triangle, and we know the three sides, we know angles. And then we have a point called, let me see whether X is on the left or on the right. Let me check. Oh yeah, X is on the left, Y is on the right, yeah. So here's a point X, and here's a point of Y. So we'll exactly locate them in a second. But now we know we have these 2 points. Somewhere we can locate, right? Okay, so now the problem is that we have a point XY on BC. So we want to compute the angle XPY. How we compute it? Actually, now we get another motivation. Because the triangle BBC is isosceles, so it motivates us to separate them into 2 congruent right triangles. So then we try to quantify the values of this angle. Let me call it gamma. The right one, let me call it delta. Right? So since this is something that is tractable, so let me call the midpoint to be M. Okay? So basically now, analogous to our first part, so for this angle XPY, we can decompose it into analyzing 2 subangles, gamma and delta. And once we get the formula for some trig values for gamma, so we can easily get a formula for delta, right? They're symmetric. And how we get a formula for gamma? So think about it. So now we put our focus on triangle BPM. For triangle BPM, so we know BM is the half of BC, right? And we know that the angle on the left is equal to A over 2. So basically for triangle BMP, for this right triangle, we know everything. We know all angles, we know all side length. So the only thing we need to do in order to determine gamma is to know the position of X. In other words, we need to know the length of like BX or MX. So once we are able to compute BX, then we know MX. So we can easily compute gamma. In particular, we can easily compute tangent value of gamma, right? And actually, computing tan of gamma is a good thing because recall that in the first part, so we calculated the tan values of alpha and beta. So now you could get a symmetric type for gamma and delta. So that could make these angles to be comparable So maybe later we can show that we can easily prove the statement we need to prove. So it seems that might be the correct direction to go. So now let me put my focus on computing Bx. Okay. To compute Bx. Now let's look at this diagram. This is the insert, right? So we need to introduce this tangent, right? X prime, parallel to AC. Okay. So how we quantify the location of X, or how we quantify the length of Bx? Actually, this is what we know. So let's look at triangle BXX prime. It's similar to triangle BCA, just because XX prime is parallel to AC, right? Because of their similarity, so we know the following thing. So the ratio of their length, so BX over BC, right? So let me denote BC to be small a, and AC to be small b, AB to be small c, okay? So it is simply equal to BX over small a. It should be equal to the ratio of their respective perimeters. Sounds good? The perimeters. So what's the perimeter of the first one? Is Bx plus Bx prime plus Xx prime divided by small a plus b plus c. So why I'm writing this form in terms of perimeter? Let's look at the numerator. So for the numerator, you see here. Let me introduce some additional points. Let me call this point, I don't know how to name it. Since we have now used D, right? Let me call it D. This is E. This is F. Okay. So we know X prime X and X prime A are both tangent to the circle. So we know that X prime D is equal to X prime D. So the two yellow lines are congruent. And analogously, we have that dx is equal to xx because both of these two blue lines are tangent to the insert, right? So how we compute X prime X? Then we can separate it to two components, AB and BC respectively. And beyond that, we have in the numerator we have BX and we have BX prime. So after this manipulation, the numerator becomes the sum of BE plus BF divided by the perimeter of triangle ABC. And we know that B and BF are tangent to the incircle. Actually, for the incircle, we know a very important result. Suppose we know the length of three sides are A, B, C, right? So then we have the closed form formula for the yellow one. We have the closed form formula for the blue one, and we have the closed form formula for the green one. Okay. So in particular for the yellow one, then we need to compute the sum of them is simply equal to A plus C minus B, right? Wow, we get a very elegant formula for the length of Bx. That is amazing. This is something we really, really love to see. Awesome. Okay, so basically now we know exactly the length of Bx. So now we are able to compute tan of gamma. Let me copy and paste this diagram here and see how we compute its value. So for tan of gamma, then we can compare it with cotangent of A over 2. Why? Because tan of gamma is equal to xm over mp. And cotangent A over 2 is equal to bm divided by mp. Okay? So we only need to compute xm divided by bm. Okay. All right. So what is xm? Actually, this is something so it's simply equal to the half of bc. So it's half of small a minus bx with the formula we just derived over bm is the half of a. Okay. All right. Let me plug bx here. So bx is equal to this fraction times a divided by a half of a. Okay. So now our job is to simplify this expression. Let's do it. So let's cancel out a and multiply both numerator and denominator by 2. And then we get this equal to 1 minus twice all. So this is what we get. And it can be further simplified as, so for the numerator, we write it as a plus c plus b minus twice of b. So it can be written as -1 plus 4b over a plus b plus c. Okay? All right, so now we get a sense that tan of gamma could be expressed in terms of the side length of triangle ABC.